We're down to our last two oral presentations for the 2014 conference. This is oral presentation 28. This is the NEST+M team from New York City, New York. It's NEST+M Team 2. This is a Mission 3B flight experiment which came back to Earth in March.
Mammalian milk and microgravity. Does bacteria growth in milk happen differently in microgravity than it does on Earth? Our team principal investigators are me, Xander Plossel, and Lenny H. Ma. Teacher facilitators are Zach Vine and Marvin C. The coordinator was Brendan Alfieri. Next.
Experimental background. Microorganisms are very important to the quality and the safety of dairy products. Bacteria are probably the most important groups of microorganisms in dairy. Pasteurization and powdered milk production does not kill all the bacteria. Spoilage in space cause significant problems. A new and better understanding of how milk and other foods boil in space might allow people to colonize different places in space. Next.
Experimental proposal. Our hypothesis is that milk will grow bacteria slower than it does on Earth in microgravity. Our proposal is that we're going to compare the bacterial growth and content of milk sample in microgravity to milk samples in full gravity. We're going to use standard methods of bacterial examination to compare the samples. We'll work with powdered milk and distilled water to limit types and amount of bacterial growth before activation. We're expecting spore-forming, heat-thriving, thermophilic, and spore-forming, heat-resistant thermoduric bacteria. They must be spore-forming to survive powderization. Next.
In our experiment, we used a type 2 fluid mixing enclosure or an FME. As you can see here in this diagram, we put 6 milliliters distilled water in volume 1 and 1.5 milliliters powdered milk in volume 2. We'll be using two methods to examine our bacteria. One method is a standard plate count. We'll color the loose solutions of samples and agar and count the colony-forming units or CFU to calculate the bacterial concentrations. Also, we will be using a reductase test. We're using methylene blue to indicate the absence of oxygen to the bacterial growth. Next, please.
Results. When the flight sample returned to Earth, it was intact. But when it got to the lab for us to examine, the screw had blown out and liquid was visible in the container. The sample was dark brown and appeared burnt. The ground sample, none of them broke, and all of the samples were milky white. For the standard plate count, which involves diluting the sample, then spreading it out over agar, incubating it, then counting the colonies. Each colony should be about one bacteria. We got about 260 colony-forming units per milliliter milk for the flight sample, which is very low, and the ground samples were getting the 10,000 colony-forming units per milliliter. For the reductase test, the ground sample took more than 8 hours to change color, which indicates a low rate of oxygen depletion. This was probably because the bacteria who were present in this situation did not use up oxygen very quickly. For the slight sample, we can't conclude anything because of the dark coloration of sample. You can't tell when the blue faded. Next.
As you can see here in this enlarged picture, the little black circle thing, which is the plug, and it blew out. Also, in the bottom right corner of the plastic bag, you can see a little bit of the milk that spilled from the FME. From the little milk that spilled from the FME, you can see that the milk coloration is brown, not the usual white. These results are not expected. Next slide, please.
Analysis. Flight sample, some likely causes of FME failure were gas pressure buildup from continued growth of bacteria. Delays between flight sample return and laboratory testing contributed to failure, and only limited conclusions were possible because of FME failure. The low standard plate count may have been a result of die-off because dead bacteria will not form colonies. The ground truth sample, you got expected high bacterial growth rates were recorded. We can't directly compare them, though there's a chance that the flight sample had a much higher bacterial growth. which caused more gas buildup and a blowout. And then they used up all the nutrients, so most of them died off. Next.
If this experiment should be done again, we can conclude that many more things. We can conclude, although we could conclude that the flight sample did not have a higher or lower rate of bacterial growth. We can conclude, however, that there was a greater gas production in the flight sample, which may indicate a greater bacterial rate of bacterial growth. If this experiment should be done again, we recommend that much more things that are not being tested should be controlled. One of them is the period of bacterial growth. The period of bacterial growth should be shorter to limit variance. Also, halting the bacterial growth before returning flight sample would make the handling much more similar. Lastly, the temperature is very important to the survival and the bacterial growth and survival and needs to be the same between these two samples. Sample examination and testing must be well organized and done quickly for biological experiments.
It's very important for this to have the bacteria stop growing before the return. It would kill them off, but then you could use a because it also preserves it, you could use a microscope to directly count them. You also have to control temperature better, because since they weren't controlled, one might have been at a better temperature for bacteria growth, which might have caused it to grow a lot more bacteria. Next. We would like to acknowledge these people, such as the New York Space Grant Consortium, Hunter College, New York University, and others.
Thank you for listening to our presentation.
Any questions for the New York City team?
Hello, I'm Mihal from Colorado. Now, obviously, when the test tube is going up in space, it gets a lot of turbulence and it shakes quite a lot. Do you think that this may have contributed to more gas buildup and the blowing out of your test tube?
Well, actually.
Okay, when it was going up, it was actually in powdered form, but when coming down, that was one of the problems. That's one of the reasons why we should have stopped it, so that when coming down, it didn't affect bacteria growth.
And also, I'd like to add, also when the SSEP when they looked at the FME, the seal was still intact. And also when the advisor at school in NEST+M, the seal was still intact. They took a picture of it, in fact. But between the period when it was taken a picture at our school to the period when we examined it in NYU, the seal broke.
It's unfortunate. I'm sorry. So, great presentation, by the way.
Thanks.
Hi guys, as you know, I'm Alex from New York. Great job on your presentation. My question is, what made you choose this experiment?
Well, actually, originally, this was one of my ideas. I was thinking about using bacteria and different sorts of cheeses, but cheeses would be too hard, so we simplified it to milk.
Thank you.
Hi, I'm Jonathan from Long Branch, New Jersey, and I have the question that, do you think that if the test samples were positive, and if they came out and the screw didn't come off, do you think that your hypothesis would be actually true?
We think that our hypothesis is partly true. We're not sure though, because the results are inconclusive. But But since the seal broke, the results for both the standard plate count and the reductive test are probably not correct. So even though the results for the standard plate count showed that the flight sample had a higher bacterial, had a lower bacterial growth, it's possible that there was a greater gas production in the flight sample between the return. But so we're not sure.
Thanks.
Hi, I'm Griffin from North Charleston, South Carolina, and I just I'm interested about the seal breaking on your experiments, because on our experiments, the sample that went into space, when it came back, it was intact, but we had almost all of the samples that were on the ground, the new ones with the screws in them, we had almost all of them break, except for one. all of those seals. And I'm wondering if you had any sort of like things on the outside of the FME before the seal broke, because when that happened with us, there was salt kind of caked all around the end cap of the FME.
I don't think we found any salt.
Yeah, there was no salt, there was nothing. It was just plain, I don't think there was anything on outside the FME, there's just that the seal broke. And there's a little liquid.
We're guessing it was just a pressure buildup.
Yeah.
Yeah, but that happened with ours on Earth, so I'm just kind of, yeah, it's pretty weird, and I'm sorry about that. It was pretty difficult to deal with. Thanks.
I'm Nora Jam, and I'm from New York City. If you could do this experiment again, what would you change?
Well, one of that in it, we would stop the bacteria growth when still on the ISS, which would kill them, but preserve them so that we could directly observe it with a microscope and count the bacteria. We would also try to keep the temperatures more controlled.
Okay, thank you.
And we also also in the central examination, if you could do this again, you'll from when we return to our school to our examination part, there should be less time because ours it was delayed for a long time, so it should be like 1 day, 1 week.
Thank you.
I think I should point out something that we were talking about yesterday, that failure is something that needs to be embraced. It did not go the way you intended it to go, but you did an excellent job in analyzing what might have gone wrong. The FME is susceptible to overpressure, and in fact that's one of the things that we look at for Step 2 review before passing on to flight safety review. And I think that, just my personal view, we learn far more from failure than we do from success. And I know that NEST+M is going to be moving forward with Mission 7, and you've done a great job in assessing what might have gone wrong and what you might do different. So I encourage you to re-propose. And that's the way real professional researchers handle something like this. So with that, let me say thank you to the New York City team.